Professor Michele Ceriotti from Laboratory of Computational Science and Modeling, EPF Lausanne, Switzerland. Michele will present his lecture, Physics-Based Machine Learning of the Electron Density. And Michele was educated at the University of Milano, where he got his BSc and then a master degree in 2006. Then he went for a postdoc in physics to Swiss Federal Institute of Technology, Zurich, and worked under supervision of Professor Michele Parinello. And after a PhD, Michele did a postdoc at the same place and went for another position from another junior research fellow at Merton College, University of Oxford, where he worked together with Professor David Manolopoulos. Next, Michele became assistant professor at EPFL, and that was in the years 2013 up to 2020. And next, he became associated professor at the Institute of Materials, EPFL. And his main scientific interests are focused on development and application of statistical sampling and machine learning algorithms to achieve predictive atomic scale modeling of molecules and materials, and to understand structure property relations. Michele is associate editor for the Journal of Chemical Physics and is a member of editorial board of Physical Review Materials, moderator of the Physics and Chemistry section at Archive, spokesperson of the Psy-K working group on statistical sampling. He organized a dozen of workshops, schools, and symposia, and serves and also as a reviewers for many journals and grant proposals. Got several prizes and awards, including 2018 IUPAC C10 Young Scientist Prize and in 2013 Walker Heine Young Investigator Award, in 2010 IBM Research Forschungspreis, and in 2010 ETH Medal for PhD thesis. Michele published more than 150 papers that have collected more than 12,500 citations, and he achieved his H index equal to 61. Delivered,
I think it's important.
Delivered more than 200 talks. And earn plenty of money, close to 10 million euro in different grants, including ERC starting grant and ERC consolidator grant. So, Michele, the screen is yours.
Thank you very much for the introduction. Even though there was really wasn't necessary to go so much in depth with all the stuff that I did, but thanks a lot. So yes, so this what I want to tell you about today is a little bit in general about the use of machine learning in the context of atomistic modeling, and specifically I want to focus on some methods that we have developed to predict the ground state electron charge density. So the general idea of what we are trying to achieve here is basically to build a surrogate model for quantum mechanics. Essentially, the idea is that quantum mechanical based techniques, electronic search methods have been extremely successful in allowing us to link the coordinates of the atoms with different types of observables, from the interatomic potential that tells us about the stability of different configurations of structures, to properties that are connected to the electron density, such as the electron density itself, effective single particle Hamiltonians, different types of dielectric response, and so on and so forth. And basically the idea is that rather than doing these predictions using electronic search methods that can be very demanding and that scale poorly with the size of the system, we try to circumvent the need for these quantum calculations by using a machine learning model itself. So I'm not going to talk about machine learning models in which you describe the type of compound that you want to synthesize, and it tells you the kind of recipe that you have to follow to make it. I'm going to really to talk about machine learning as a shortcut to achieve the same type of mechanistic insights that you could achieve by solving accurately some kind of accurate approximation of the electronic Schrödinger equation. So one kind of philosophical point that I want to make is that machine learning techniques, machine learning methods tend, unfortunately, in my opinion, to have a little bit of a branding problem. So when it's a little bit like ChatGPT. When you use a ChatGPT, there are many choices that have been made for you: the type of model, the way the model has been trained, the way you interact with the model, the way you basically incorporate it into your workflow. And then this gives something that works potentially also very well, but where you are not really in control of how the model is built. So over the past few years, we have been sort of trying to deconstruct these machine learning models, trying to understand all the mathematical building blocks that enter the construction of a machine learning model for atomistic problems. And you can, I guess you can imagine where this is going. Basically, the idea is to make modelers and users of these machine learning models be able to mix their own, to combine these ingredients in the way that is most suitable for the problem that they are trying to solve. So from this perspective, I think it helps a lot to take kind of one step back and trying to understand what are the mathematical structures that we are building into a machine learning model. Because at the end of the day, if we are going to make a prediction based on a machine learning model that should reproduce the results of a physics-based calculation, the machine learning model itself must contain sufficient mathematical flexibility to describe correlations, long-range interactions, and all of these kind of physical mechanisms that determine the structure property relations. So from the point of view of the description of the inputs, so what are the objects that we're trying to describe? Well, these are assemblies of atoms and molecules. And so from a mathematical perspective, we can regard these molecules or these crystal structures as point clouds, essentially collections of three-dimensional points decorated with a label that specifies whether the atom in a certain point is a carbon, an oxygen, a hydrogen, or whatever else. And another way of looking at this, which I guess is more natural to organic chemists, is to regard molecules as graphs, where basically the essential building block is the collection of bonds, or basically edges in a graph language that connect pairs of atoms, usually only up to a given cutoff. So from this mathematical viewpoint, what we're trying to do then is to find the mapping between this description of molecules and materials as decorated point clouds, and the properties that we would predict with a quantum calculation. Now, the fact that we are trying to describe molecules and materials rather than, a truck driving on the highway means that this mapping must obey some properties that are basically a requirement of the physical nature of the mapping between the structure and the property. So, for example, in the vast majority of cases, the properties that you can compute from a self-consistent electronic structure calculation for a given position of the atoms are smooth with respect to infinitesimal displacements of the atoms. And this smoothness doesn't only allow us, for example, to compute easily, for example, the forces given the potential, but also underlies the very fact that we can expect to be able to build a machine learning model. If the structure property relations could have arbitrarily large variations, arbitrarily irregular behavior, we would need an extremely large amount of data to be able to train a model. Thanks to the fact that the connection between structures and properties tends to be smooth, a relatively small amount of data is sufficient to achieve very accurate approximation of the structure property relationships. Another requirement that seems trivial, but actually it's not trivial, and there are a number of sort of very fun mathematical papers that we have been working on in my group in the past couple of years, is the requirement that this mapping is complete, or probably more precisely injective. So if I have two structures that are different and that can have different properties, I have to make sure that my machine learning model is capable of distinguishing them. And what makes this requirement non-trivial is that at the same time, it's very beneficial to require that the mapping is consistent with symmetry. And here I'm not speaking about special symmetries. I'm not speaking about point group or space group symmetries. I'm just saying if I have a molecule in free space, its energy shouldn't depend on the absolute orientation of the coordinate system. If I have a FCC metal, the energy of that metal, the energy per atom of that metal doesn't depend on whether I pick the primitive cell or the conventional FCC unit cell. So basically, we want the machine learning model to automatically incorporate all of these symmetries. And this leads to pretty non-trivial consequences that can actually generate models that are not complete, that are not capable of differentiating structures that actually are not related by symmetry. And finally, something which is perhaps less obvious, but it's actually very much rooted in physical principles. For instance, the nearsightedness principle from Walter Kohn, is the idea of building models in an additive manner. So, for example, if I want to predict the total energy of a structure, I would do that as a sum of atom-centered contributions. And the reason why this is useful is, again, an argument of dimensionality reduction. So if I was trying to build a machine learning model that predicts the properties of a material in terms of the coordinates of all of its atoms, let's say that we have a unit cell with 100 atoms, we would need to basically be able to approximate a function of 300 coordinates. And that would require a huge amount of data. If instead we break down that energy into terms that only depend on local information, let's say on the correlation between atomic positions up to 3 angstrom, then it is a much more feasible proposition to be able to approximate the energy of that system. And so basically, all of these physical requirements translate into constraints on the functional form of the machine learning models that we can use. For example, if you want a model to be additive, we should write the energy or any property y of a structure in terms of a sum of contributions that are connected to atom-centered environments. So basically, the functional form that I try to build should only depend on the relative position of atoms within a certain sphere around each atom in the structure. And if I want my model to be symmetric, it should automatically incorporate equivariant properties, such as the fact if my property is a vector and I predict that property for a rotated version of my system, then this should automatically yield the vector upon which the rotation has acted. So, and the same, I mean, for example, I would like the model to be invariant to the order by which I present the coordinates of the atoms. Also, this should be automatically built in the mathematical structure of the model. So it turns out, and this is something on which we have been working on since at least 2018, it turns out that the vast majority of the machine learning models that people have been using over the past decade, if you're a little bit familiar with the field, stuff like Baylor-Parinello symmetry functions, smooth overlap of atomic position descriptors, bond order potentials, and bag of bonds descriptors. There are a number of different frameworks that people have been using, and actually, when you look at them through the lens of symmetry, you realize that they are actually pretty much doing the same thing, and that the vast majority of the models that are in use today can be seen as building upon correlations of the neighbor density. So basically, I sit on an atom, I look at the probability of finding a neighbor at a certain distance, and then I build tensor products of this neighbor density, and I symmetrize, for example, over the continuous rotation group. By this symmetrization, I make my model invariant to rotations. And by building higher and higher orders of correlations, I build in more and more information about the structure, and I basically get a model that is more descriptive and capable of learning more complicated properties that depend on more complicated correlations between the atomic positions. You can actually generalize, and I will return to this, you can generalize this construction to make it equivariant rather than invariant. And by doing this, you can build machine learning models that are adapted to the symmetry of different irreducible representation of O3. You can also, and this is something I will not have the time to discuss, but you can also go beyond a purely local description of a structure. And we do this sort of by building Ewald-based descriptors that incorporate information in the far field by basically building descriptors that correspond to the long-range behavior of Coulomb interactions, van der Waals, and whatever type of asymptotic behavior you want to build in. And finally, we have also shown recently that even so-called message passing machine learning schemes can be understood through the lens of these correlations of the neighbor density. So for those of you who are familiar with statistical mechanics and with the construction of descriptors of liquids in terms of pair and three-body correlation functions, what I'm saying is that the vast majority of the machine learning models that are in use today can be understood as using those correlation functions as the building blocks of the model. And I find this very pleasing that somehow we have rediscovered the same building blocks that are at the basis of statistical mechanics of liquids. So the reason why it is important to build models that are symmetry adapted is that there are properties, say, for example, NMR chemical shieldings that are scalars, and so you can get away with just building models that are invariant to rotations, which is relatively simple. But there are other properties, for example, the polarizability, that are intrinsically tensorial. And then your machine learning model should be consistent with the transformation properties of a tensor. And if you want to learn properties that are even more complicated, for example, an effective single particle Hamiltonian, you need a machine learning model that intrinsically knows about molecular orbital theory. You want a machine learning model that knows that if you predict the properties of benzene, that is D6H, you want the model to know that there should be some pairs of orbitals that are degenerate. It's just something which is such a fundamental property of the geometry of space that there is no point in having the machine learning model learn it through exposure to data. You can basically build it into the architecture of the model. So the way you can do this, it's actually by building descriptors that are themselves adapted to the symmetry of the problem. So for example, let's say that we want to learn a dipole moment. A dipole moment is a vector. And what I want is that if I rotate my molecule, the dipole moment, my prediction for the dipole moment should rotate exactly in the same way. And one possible way of achieving this, and in many ways, the only way of achieving this is to build a basis of descriptors for my properties. And here I'm using this sort of fancy notation. What I'm meaning here is that I want to describe a molecule A, and I will have a bunch of descriptors that I'm calling Q. These are discrete index that labels a set of descriptors for the molecule. But I also need a geometric descriptor that basically tells me whether I'm predicting the X, Y, or Z coordinate component of the dipole moment. So basically, if I want a model that is symmetry adapted, it should simultaneously describe the structure and the symmetry properties of my target. And then you need to build, in this case, I'm just building linear regression. This is a fancy way of writing a linear regression model. Basically, my dipole is a combination of some coefficients, one for each feature, multiplied by the features that describe the molecule. And then what I need is to construct descriptors that rotate in the right way when I rotate the molecule. If I can build descriptors that rotate as by the application of a rotation matrix, then this type of model will automatically be equivariant to rotations. And this fundamental idea can be generalized, can be used to learn vectors, but can also be generalized to learn arbitrary properties with an arbitrary behavior under symmetry, just by decomposing the property in components that transform like spherical harmonics that are the irreps of the continuous rotation group. Okay, if you are still with me, the point is we have a machine learning framework that allows us to learn targets that transform like spherical harmonics. And actually, this is ideal if we want to learn the electron density, because again, to get a model that is transferable, where basically I can train the model on small molecules and then make a prediction for a solid, it's very useful to build a model that decomposes my target in atom-centered contributions. So I want basically to expand the atom density into atom-centered contributions to the atom density. So basically, I will expand my density as a sum of atomic contributions, and I will expand my atomic contributions in a atom-centered basis, so radial functions and spherical harmonics. But now the coefficients in this expansion transform like spherical harmonics. And so if I want to build a machine learning model that predicts these coefficients, it better be adapted to the rotational properties of the spherical harmonics. And through this construction that I sort of sketched, I don't expect that you have followed all the details, but I hope that you have got the core idea, which is that we describe an environment in terms of correlations of the neighbor densities, and we project these correlations onto their irreducible components. We basically decompose them in irreducible rotational components that we can then use as a basis to expand symmetry adapted functions. Now, learning the charge density in this way is actually really challenging from a technical point of view, because this basis is not orthogonal. The orbitals on different atoms have a non-zero overlap, which basically means that all of these machine learning problems are coupled to each other through the overlap matrix. It's also challenging because decomposing accurately the electron density is not easy, particularly if you want to reach the same level of precision that you get from an electronic structure method. But luckily, in quantum chemistry, people have been expanding the density in something which is called the resolution of the identity basis. And so we can basically exploit these developments in quantum chemistry and use a resolution of the identity basis to expand the charge density from an electronic structure calculation and then learn it. And the point is that thanks to this atom-centered decomposition idea, we can learn on essentially small organic molecules and then make a prediction that is actually pretty darn accurate on something which is much, much larger. We can go on and predict the charge density for a polypeptide having only trained on small organic molecules. So once you have the charge density, you can do a lot of things. I guess that, in the context of crystallography, you could try to use these to predict more accurately the diffraction pattern. We can use it to predict the electrostatic energy surface, which is useful to sort of qualitatively understand the interactions between charged or neutral residues. And, I want to stress that actually all of this framework is very, very general and very transferable. You can apply it to molecules in the gas phase, but you can also apply it to crystals and to systems in the condensate phase. You just have to be a little bit careful with how you define the overlap between the different basis functions. But again, this is something that has been already worked out very carefully by people who do electronic structure calculations. So we just have to do the same thing, make sure that we're using the same convention, basically. And then you can, for example, make predictions for the charge density in ice. And what is interesting about this is that actually models, in our experience, tend to be considerably more transferable than models that don't use the electron density. So this is one core issue. If you want to use this electron density as an intermediate to predict something else, the electrostatic energy, the exchange correlation functional, or whatever, you need to ask yourself, and actually, many people who are working on predicting the electron density don't do this step. You should ask yourself, how hard would it be to predict directly the property that I really care about? If I want to predict the exchange correlation energy, isn't it better to just build a machine learning model for the exchange correlation energy? And actually, it turns out that at least for some classes of systems, spoiler alert, those which are dominated by electrostatics, predicting the electron charge density as an intermediate and then using the predicted electron density to compute the electrostatic energy or the exchange correlation energy leads to a smaller error than if you tried to predict directly these scalar quantities. So in general, to sort of try to give you a little bit an outlook of where this is going beyond predicting the charge density, I think that something which is very interesting, if at the end of the day you want to use machine learning in the context of quantum chemistry and electronic structure theory, something that is very interesting is trying to mix and match. So there is no reason why you should limit yourself to going all the way from, you shouldn't limit yourself to do only machine learning or only electronic structure methods. You could, for example, predict the charge density by machine learning, and then use a physics-based expression to predict electrostatics. This is what I just did in my previous slide. And there are many things that you can try then, and I want to give you an example, which I think is sort of cute. So here, what we're trying to do, it's perhaps a little bit esoteric, but basically we want to predict the energy of some electrons in a very, very hot environment, 50,000 Kelvin. We are speaking of the core of a young Jupiter, okay? And so if you want to predict the electronic properties of matter in those kind of conditions, you cannot assume that the electrons are frozen in the ground state. You need to use a free energy functional for the electrons. And basically, if you wanted to build a machine learning potential, you would have to predict a different machine learning potential depending on the temperature of the electrons. So what we are doing here is use a physics-based expression, basically a perturbative expansion of the Mermin functional, to compute the finite temperature electron free energy in terms exclusively of ground state properties, the ground state energy and the ground state electron density of energy levels. And so what is nice is that basically, this integral is, you can recognize the electronic entropy, you can recognize the electronic excitations, and we are computing by machine learning some of the ingredients, but then we are combining them with a chip to compute a physics-based expression. And the result of this is a model that is more transferable, because with a single training exercise, we can predict the free energy functional, and then, for example, the phase diagram, the equation of states of matter, up to, and actually even above 50,000 Kelvin. So, if you want to try any of these for yourself, we are very much fond of open science and open source. Everything is available on GitHub with different levels of documentation. Some of this code is pretty horrendous, but it's open at least. And we are working on basically making it more user-friendly, and we try always to make everything very modular so that at least some of the components are decently usable. And basically, that's all that I wanted to tell you. And I just, before I finish, I just want to make sure that I show you the faces of the people who have been doing a lot of the work that I told you about, and the logos of the funding bodies who are paying our bills. And if you want to know more, we have a couple of reviews that we published recently that can give you an idea about this whole systematic construction of descriptors for atomistic machine learning, and some of these ideas about mixing physics-based and data-driven modeling to build models that are accurate but also interpretable. So thank you for your attention.
Thank you very much, Michele, for this excellent lecture, which is now open for questions and comments. And before first questions will appear on the chat, maybe I will take this opportunity and ask you about ice, in which I'm personally interested in. This electron density you are showing, for which form of ice you got it? I mean, there are like 20 forms of ice, and with these methods, machine learning methods, can you predict existence of particular forms in particular thermodynamic conditions? Can you obtain electron density for those 20 known forms of ice, and maybe for next 20 unknown yet?
So that's an excellent question. So can you? Yes. Have we done it already? No. This is ICE 1H, and we were basically here. What we wanted to probe was the transferability of the model, really. So one of the something we have been playing around with predicting the electron density for 5 years now, and a very frustrating thing has been that for quite some time, whenever we used this density to predict something else, we were finding an accuracy that was worse than doing a direct prediction of that quantity. So here we really wanted to sort of demonstrate that for some classes of systems, going through density is a worthwhile exercise. Now, what you are asking about is also very interesting, and just something that we didn't have the opportunity to do, which is if you actually want the density, for example, because you want to have a more accurate estimate of the I don't know, the scattering, the structure factor or whatever, then it's kind of silly to have a machine learning potential run some sophisticated structure search and then having to go back to DFT to get the charge density. So yes, it would be possible and would be very interesting to see how far you can go with predicting the charge density. Particularly, I think it would be very interesting to look at ice 10 and all the high pressure phases of ice where protons are delocalized, are mobile, and it becomes probably much harder to get a good prediction of the charge density.
Michele, we are doing this from experimental point of view, so maybe there will be a chance to compare your prediction with experimental outcome.
Yeah, that would be really, really cool.
Okay, we have some comments and questions written on chat. Paulina, can you read next one?
Yes. Florian Clemens, I will just reverse the two comments. Brilliant talk. And then a question. Which types of atoms have you managed to train the machine for and benchmarked the densities against full quantum mechanical results? How do electronically flexible metals with metal organics behaves?
Oh, okay. So this far, so I have sort of actually should point that if you look at the more recent work on this electron density prediction, I've all done in collaboration with Dr. Mariana Rossi from MPG Hamburg. So, you know, a lot of the credit for this more recent work goes to her and to her postdoc and to her collaborators, basically. And so basically what Mariana and Adam Lewis have been doing is testing these on different types of systems. And I think we have tests for aluminum, for ice, for a hybrid perovskite, and they have been doing some stuff on twisted bilayer graphenes. So this is pretty flexible. An interesting question is more than which atoms could you do this for, is how many atoms simultaneously, how many atom types simultaneously. So this is a very difficult problem because basically when you build these atom correlation functions, the chemical nature of the atoms is basically each type of atom. So I think that, you know, for this audience, you might be led to think that we are expanding the charge density. We are not expanding the charge density. We are just putting Gaussians on the atoms. I mean, here I'm predicting the charge density, but when I build the descriptors, we are just using a completely fictitious density where I put Gaussians on the neighbors. And then we use a separate channel, a separate density for each type of atom. This means that when we build correlations, the complexity of the problem grows exponentially with the dimensionality. If I have just pair correlations, I have as many densities as I have types of atoms. If I look at three-body correlations, which are two neighbors, I have the number of elements squared. If I look at four-body, three-neighbor correlations, I have number of elements to the power 3. So this becomes very taxing to when you have many types of atoms. Now, we haven't done this for the charge density, but for the potential, we have been, there is an archive paper that we put basically in December last year, in which we learn a machine learning potential for 25 transition metals simultaneously. So we can do simulations where we compute the interatomic potential for 25 D block transition metals at the same time. In principle, this might also work for the charge density. I don't want to do it because it will really be a nightmare in terms of the number of coefficients that we need to learn.
The next question is from Hans Bitbirgi about the smoothness. Some physical properties go through catastrophic situation, example, change of electronic state. How can you handle this?
Yes, no, that's a very good question. So basically, the problem might be when you get something like, so if you start looking into excited states, so if you try to do machine learning for excited states, things become much trickier because you have to deal with conical intersections and you need to deal with all of that stuff. When you deal with ground state properties, usually if you formulate the problem appropriately, usually you can get a smooth potential energy surface. If you don't, if you have a problem in which you have a discontinuity, it can become interesting. This is one of the cases in which it can be interesting to go through a proxy of the property that you want to predict. For example, rather than predicting, something that we're doing is rather than predicting the Homo-Lumo gap, what you could do is learn an effective single particle Hamiltonian, and then you diagonalize that effective single particle Hamiltonian and you get the Homo-Lumo gap from there. The same could go for excited states. The matrix elements of an effective single particle Hamiltonian might be more local and smoother than the electronic energy levels. So that might be one way to deal with properties that have an irregular or a very delocalized behavior. But yes, properties that are intrinsically discontinuous or properties that are intrinsically very non-local are a challenge for current machine learning methods.
Next question is from Vikas. Thanks for the nice presentation. Would you like to say something about crystal structure prediction for non-central symmetric space group modeling via machine learning and deep learning?
Okay, so I can say something. I'm not sure it's you tell me if this is if I'm misinterpreting your question. So there is nothing in our framework that relies on the existence of spatial symmetries. Okay, actually, something which is really nice of our framework is that point group or space group symmetries are a subgroup of the combination of rotations, translations, and atom label permutations. And this means that the model, if you present to the model a symmetric structure, the model will be able to exploit this symmetry. If you present to the model a structure that is not symmetric, the model will be able to learn the properties of that non-symmetric structure. And actually, there is more to that. For example, our models know about Jahn-Teller theorem. So if you, unfortunately I don't have, I think I don't have the figure for that. But if you look at this paper where we learn an effective single particle Hamiltonian for benzene. So if you learn, if you predict the eigenvalues for the symmetric D6H structure, you get the degeneracies that you should have. And if you start deforming the structure of benzene, you get basically symmetry breaking in exactly the way that is predicted by Jahn-Teller theorem. So you know, if you lower the symmetry along a certain direction, you get the splittings and the first or second order changes in the energy levels that are predicted by Jahn-Teller theorem. So there is nothing special about symmetric or non-centrosymmetric space groups. If the symmetries are there, the model will exploit them. If they are not there, that's not an issue.
Mm-hmm.
I have a following question, but the models you are building, they predict some properties like electron density or electrostatic potential for a given system, but you have to input, what's the input, the coordinates of atoms, or you also are able to predict, no, so you are not predicting the coordinates of atoms, it's already external information.
Yes, so this is a very important, this actually is a very important point. So you have to really think that what we're doing is, so I, you know, my background is actually, I've done a lot of ab initio molecular dynamics earlier in my career, and I have burned a disproportionate amount of CPU hours to run those ab initio molecular dynamics calculations, and I've produced a terrible amount of CO2 doing those calculations. So my objective here is basically to be able to do the same, but for cheap. Okay, so we predict the properties of a specific configuration of the atoms, and actually this is not problematic, but this is something that you have to keep in mind if instead you want to make a prediction of an experimental property. Because typically your experimental property will be averaged over thermal fluctuations. If you know, if you want to do the, if you want to predict the electron density that you measure with a diffraction experiment, that's averaged over thermal and quantum fluctuations of the nuclei. Okay, we only predict the electron density for one configuration of the nuclei. So the idea, and actually we have done these, for example, for NMR chemical shieldings. What you should do is you run molecular dynamics using a machine learning potential to sample configurations that are consistent with thermal and 0-point energy fluctuations. For each of those, you compute chemical shieldings or the electron density, and then you have the ensemble average of those instantaneous properties, and that is what you can compare with experiment.
So that means that there are existing already methods using machine learning in molecular dynamics, or it's your goal for the future?
Yeah, no, this is, it's actually, so in 2010...
I mean, electron density kind of...
Well, our method can do it. We aren't doing it because it's still kind of expensive, okay? So one of the issues when you go from predicting a potential to predicting something like the electron density is that you need to start predict a lot of coefficients. So even though this is way faster than an electronic structure calculation, so for example, we can predict a protein with 1,000 atoms, we can predict DFT quality electron density in a couple of minutes, rather
for a
than
given atomic configuration,
yes,
positions. But
you
how
can
to
do
then
the
run
prediction in
dynamics?
a couple of you can do make the prediction in a couple of minutes. Now, if you wanted, we can do molecular dynamics quite cheaply, but if you start wanting to compute 10,000 snapshots so that you can average over them, it starts becoming a little bit more expensive. So it's something that we haven't done yet, but it's definitely feasible. It's not. It's definitely cheaper than what I would have done 5 years ago, running ab initio molecular dynamics for that same system. So,
but during the molecular dynamics itself, you are also using your prediction for electron density, or these are like a standard kind of molecular dynamics?
So I would probably do. I would probably use a standard machine learning potential trained on DFT that directly give me the potential, and
okay,
then
for dynamics. Okay.
yeah, because I mean, at the end of the day, you don't need to compute the electron density. If your objective is compute the ensemble averaged electron density, it's kind of silly to compute it every half a femtosecond, right?
Yeah,
You
that's
can
true.
compute it every 100 femtoseconds, so you have more efficient statistical sampling, and that is what I would do.
We have question with Hans Bitterbergi. If you worked with complete decorated graphs, you would not have to worry about O3, but only about molecular and permutational symmetries. What keeps you from doing this? Yeah, that was awesome.
Okay, so this is a let me see if I have a oh no, I don't have it, sorry. Not on this deck of slides. Okay, so there are many layers to unpeel in this question. So first of all, if you want to predict a property that is equivariant, or a field like the density expanded in equivariant components, you would still have to worry about O3, because your target property has a prescribed rotational symmetry, and you need to incorporate that rotational symmetry in your prediction. Now, if you work with graphs, there is graph and graph. So if you work with graphs that are distance decorated, so there is, for example, this very popular graph convolution network, which is called SNET, that uses molecular graphs in which the edges are decorated by the interatomic distance. Now, it turns out that even though this is a very powerful framework, and it's basically capable of differentiating a lot of structures that are difficult to distinguish by other methods, it's not a complete description. And we have a paper from a year ago. You can basically look up I have this PhD student, his surname is Pozniakov, and he has been basically killing methods for a couple of years, and basically showing building geometric counterexamples that are not distinguished by different type of machine learning frameworks. And one of the things that he has shown last year is that for graph convolutional network that are invariant through the because they decorate the graph only with invariant distance information, you can build graphs that are indistinguishable by the graph convolutional network.
And maybe following a question, and how local your atom types are, how far from the central atom you are going?
This is another excellent question. So it depends. So if you are looking at something like small organic molecules, you can actually, and you are interested in learning the atomization energy, you can get pretty accurate model with very short cutoffs, like 2.5 angstrom. And
so meaning the first neighbors, right?
Yeah, exactly.
Maybe second.
Exactly. But if you are interested in something that is dominated by electrostatics, no cutoff will ever suffice, right? Because basically it's very, very slowly converging. And this is where we are trying to develop this framework that we call LODE, long distance equivariance, that instead basically tries to build descriptors in reciprocal space so that we can incorporate long distance information, because you can't really truncate these to short range information. Now I see in the chat a question about chirality.
Yeah.
So yes, if you use distances only, of course you miss chirality, but you miss more than chirality. You can have structures that are not enantiomers and still cannot be distinguished by a distance decorated graph. If you use correlation, basically neighbor correlation functions, you can, if you want, you can distinguish chirality, because basically you can get descriptors that are odd with. Actually, you can build descriptors that are pseudoscalars, and those are ideal to learn about chirality, because basically those are descriptors that change sign when you flip about the origin.
I have maybe naive question. You said that there is a limit of the number of atom types you may have when you train your machine. Can you combine different results? I mean, let's say that you have one set of molecules containing one kind of atom types, and you train your machine, then you have another set, and you have yet another trained machine, and can combine them both after the training.
So you are basically asking if you can do something like the mixing rules for Lennard-Jones potentials,
Yes,
right?
yes.
So
assuming that you already assume that some properties are local, so
so I really invite you to read this preprint from 2000 from December. The first author is Natasha Lopanitsina, and what we're doing there is something that goes a little bit in that direction, and basically what we're doing is we are doing a sort of we call it an alchemical compression. So we take this 80-dimensional, well, in this case we have 25 elements, so we take this 25-dimensional chemical space and we project it down to 3 dimensions. So we are not describing the elements as completely distinct entities. Now, this is going to sound very, like I'm a charlatan, but essentially what we're doing is literally equivalent to saying that we have classical elements, that we have water, earth, and air, and we learn the behavior of these 3 classical elements, and simultaneously we learn the composition of the 25 transition metals in terms of these 3 classical elements. This makes it possible to learn much more efficiently, because you basically learn in a reduced dimensionality space. You can basically learn the similarity in behavior of the different elements. And in the paper, we do a very, I really think it's a very interesting exercise. So for historical reasons, we basically didn't think too well what we wanted to do initially. And so we only considered 25 transition metals. So we left out 5. And I mean, okay, technetium, okay, it's not really important, but we left out osmium and rhenium. And basically, you can interpolate in this 3-dimensional space, and you can interpolate between iridium and tungsten. And even if we have never trained on rhenium and osmium, by interpolating between the behavior of the neighboring elements in the periodic table, we can actually get pretty decent predictions. So this, I think, goes a little bit in the direction of what you were asking of combining learning from different exercises. Here we're basically interpolating in the periodic table to make a prediction for elements that the model has never seen before.
Mm-hmm.
Yes. Hans Beth is writing. Yes, I like to think of the machine learning methods as very elaborate interpolation schemes. If so, how do you avoid dangerous extrapolation?
This is an excellent question again. So you avoid extrapolation in two ways. So first, even though you might be nominally extrapolating, in practice, based on the choice of descriptors and the choice of locality in your model, you might actually be interpolating. A good example is if I train a model on a liquid phase, a solid phase, and on small simulations that contain an interface between a solid and a liquid, now I can make a large simulation box that contains a solid-liquid interface. The system has never seen before a large solid-liquid system, but it has already seen all the ingredients, and so I'm not really extrapolating, I'm just interpolating. So basically, one way of avoiding extrapolation is through locality. And the other way to avoid extrapolation is to use uncertainty quantification. So since all of these machine learning methods are rooted in statistical approximation theory, you can often associate an uncertainty with your predictions. And then when your model is truly extrapolating, your predicted uncertainty shoots up, and then you know that there is a problem and you know that you have to do something about it. So I sound a little bit preachy, and I have to admit that I can't even convince my own students to do this. But I think that every time you make a machine learning prediction, you should have an uncertainty associated with it, because it is possible to do uncertainty quantification. And I think that we have already enough errors in our simulations without also adding uncontrolled extrapolation errors. And so doing uncertainty quantification is a good way, if not to avoid extrapolation, at least to know when you are extrapolating.
Mm-hmm. Thank you very much.
I have a following question.
Yes, please do, Paulina.
So you said that you are able to predict electron density or charge density of the quality of DFT level, let's say. But how you judge the quality of your prediction? How you compare electron densities and
Yes, no, for sure. So there are different metrics that you can use. So we use a metric which is basically a root mean basically it's an L square norm normalized over the number of electrons. So in a certain sense, is the fraction of electrons that are wrong. Or you can
somehow it's like a general descriptor, or you can somehow localize how well you describe the core region, the valence region.
You can compute it. So actually here, this isosurface, this cut shows this delta rho. This is literally the difference between the true density and the predicted density. And you see the scale, it's really, we are in the ballpark of 10 to the minus 4 electrons per Angstrom cube or smaller.
I wonder if we can do the following exercise, and then on the basis of your electron density, apply all the analysis which Angel was showing us, and then check how good they are when you compare to the one done directly on the computed wave function or something.
Yes, no, absolutely. So my colleague, so another colleague with whom I'm collaborating on this project is Professor Clémence Courmin-Boeuf, and she's a proper chemist. Contrary to me, I'm in material science, and I'm a little bit more of a condensed matter physicist, I think. And so she's a proper chemist, and she's using this framework first to also predict other fields like on top densities, a number of other descriptors, for example, local descriptors of electron correlation. And she's using the predicted density to compute some bond order indicators. And I'm not an expert, so but yes, she's using for those kind of things. And given that most of those descriptors are sort of aiming for a qualitative description of the chemical bond,
Okay.
these tend to work very, very well.
Mm-hmm.
Mm-hmm.
And another question: when you were training to predict organic molecules, I mean charge density of organic molecules, how you dealt with the situation that some atom types are present more often in the molecules than the others? Let's say aliphatic carbons are very common, but carboxylic group is rare, or this kind of problems.
Okay, so I mean, you could regard that. So this basically. So this touches upon a question, which is how do you define your figure of merit for your training? So if you use an L-square norm to optimize your machine learning model, and you just select your training structures at random from a data set that is representative of the kind of structure that you want to describe, you will have overrepresentation of those type of configurations. And that might be good, because if they are very common, it's very important that you predict them well.
Yeah, but some properties depend on those uncommon functional groups, not on the bulk.
Then you have to, for example, what you can do is you pick your training structures. Something that we do is called furthest point sampling, which basically tries to extract the most diverse set of structures from a pool of candidates. This tends to train your model on the more exotic functional groups and the more exotic functions, structures.
Mm-hmm.
And then you can also use a different loss. For example, you can use an infinity norm that basically tries to minimize the maximum error that you're making. And this also helps getting a model that is more, that is better behaved when you feed it something unusual. But no, that's a very good question. It underscores that in machine learning, like everywhere, you have to know what you want in order to get it. So if you have a clear idea of what you need for your problem, this is why I was making the case for sort of going away from Smirnoff Ice kind of models that are prepared and everything has been chosen for you. If you know what you want, you should be able to assemble a machine learning model, picking the best loss, picking the best strategy to select training structures, and then you can get a machine learning model that addresses your problem in the best possible way.
Thanks.
Paulina, all questions from you?
At the moment, yes.
Okay. As I do not see more questions to Michele, Thank you very much, Michele, for this brilliant lecture and very interesting discussion.